Welcome back to the data refinery. We're transforming raw vehicle data into analytical gold using open source tools that outperform commercial solutions. Let's engineer production grade data quality. So why does industrial grade cleaning matter? Well, one bad sensor can corrupt 10,000 predictions. We'll implement statistical anomaly detection, sensor-specific validation rule, and automated data lineage tracking. The first data cleaning task will be our streaming data quality with Spark. In this, we're going to read from the telemetry stream, apply some data quality rules, and write the results and errors to the corresponding Kafka topic. And in case you want to know, like, one data quality rule is dead letter Q. The second data cleaning task is the time series specific cleaning. Here we're using a materialized view from TimescaleDB, which, remember, is our Postgres instance installation with the timescale extension enabled for time series data. The next data cleaning task is our automated anomaly detection, and we basically have a DB scan clustering to find and detect outliers that could indicate anomalies. And here's a pro tip: we can run these transformations directly on Kafka streams using Spark structured streaming for real-time cleaning. Moving on to our next topic, which is going to be feature engineering. Okay, so in this portion, we're moving beyond basic modeling. We're going to create predictive features that capture the vehicle health signature, such as extracting the time series feature, as shown in the previous slide. And another set of feature set we're going to look at is our predictive maintenance feature, where we calculate the remaining useful life for each vehicle. And another feature set that's very important to mention is basically going to be composed of both quantitative measured values and kind of some other qualitative context, and that's going to be our driver behavior scoring. Here we do use a G-force based calculation to get and detect some of the hard turns and hard brake, and we can enrich that data with additional metadata and additional context to get an overall more comprehensive and holistic score for each driver. Now, moving on to our next feature set, which is going to really come into play when calculating the routes. And these are kind of like our geospatial features. And these geospatial features, we can start off by getting the optimal distance and getting the actual distance and creating a variable for the route efficiency. Now, the next thing I want to talk about is our storage optimization. In our storage, we're using a multi-tier storage architecture composed of a hot, warm, and cold. In our hot storage, this is where we put the TimescaleDB hypertables. These are tables that are optimized for time series real-time data. And with these tables, we can configure various things, especially the data retention policy. So we can set it to however long. The next storage is the warm storage. Now, the data retention from the warm storage is typically longer than the hot storage and shorter than the cold storage. This is for less frequently accessed data, which we're storing as a Parquet file in MinIO. So think of it as your Parquet file in like your S3 bucket. And the last but certainly not the least is our compressed archives, which is our cold storage. and these are basically stored as kind of like compressed Parquet file, which we can access using DuckDB. This is our least access data. Think of it as almost like our backup tapes if you're a little bit more old school. And in this one, it's also our cheapest data if you look at our chart in terms of costs. So we have our most expensive being the hot storage, and that's going to be our higher performance data from SSD, and our least expensive is the cold. Oh, I would be remiss not to mention the orchestration. We're automating our pipeline with Prefix, which kind of comes with enterprise grade scheduling right out of the box, and we can basically implement distributed processing using task runner. And another good thing about Prefix or our orchestration system is that we can deploy it as a Kubernetes cron job with that command at the end. So another thing to mention is the monitoring stack. We have 3 different layers: Grafana to monitor our real-time pipeline metrics, Prometheus to monitor kind of our operational and orchestration performance, and MLflow for our like machine learning and our feature lineage tracking. So all those feature engineering you mentioned earlier can be monitored with MLflow. And that's it. We've built the framework of a data transformation pipeline that processes 1 million plus events per minute on a single server. And this is something requiring $10,000 per month in cloud services. These open source patterns are used by companies like Tesla and Rivian for their fleets. Ready to optimize real vehicles? Star our GitHub repo, subscribe for next week's dive, and comment your toughest data quality challenge. Let's build the future of transportation efficient, open, and data driven. Thanks for watching. Bye. Hello again. I wanted to go over a guide for creating optimized storage, in this case the time series storage on TimescaleDB. Now remember, TimescaleDB is going to be the extension running on our Postgres container. So let's look at what's running in Docker. We have all the containers up and running, but this particular short demonstration is going to be focused on the TimescaleDB container, which has the basically it's Postgres with TimescaleDB extension. Now we want to be able to ensure we have a connection to that database container. There are 2 methods that I test here: a direct connection with 𝗁𝗃𝗃𝗃𝗃 module, and a connection with that 𝗁𝗂𝗁𝗃𝗃𝗃𝗃 API. So both connections were successful, or they connected. And for this demonstration, I'll be using the 𝗁𝗂𝗁𝗃𝗃𝗃. This create extension is the SQL that would basically enable the extension on our Postgres installation. This container that is in the fleet optimization project already has the extension enabled by default, so there's kind of like really no need to run it. For demonstration purposes, I'll enable it, and if it wasn't there before, or if you were spinning just a regular Postgres installation, that would be how you would enable the extension. And it was enabled, which we can also check. And the next step is to basically have a regular table. So we have this vehicle telemetry. It's kind of like a Y table design, and it has the time, which is going to be our timestamp column, and it's a regular table that we create on the Postgres, and we can check that it's created directly using a select query. But after creating the table, we can now basically convert that table to a hypertable, and there are a few commands that you can pass on to that conversion. Obviously you can set the partitioning for the time, and you can also set the chunk interval. Let's say we were starting basic, so we put the minimum amount for the create hypertable to get a hypertable, which will automatically partition the table for us according to the time series or timestamp, and allow us to do some real-time analysis. So we've kind of converted that table to a hypertable. As part of the verification, there's this SQL that we can run to get some information on that hypertable. Right now there isn't anything, but if we had more data in it, we would see a creation with different levels of, or different amounts of chunks. You can insert the data and query the data to see how it gets stored or displayed on the hypertable. Right now I'm only doing like a couple of records inserted, but let's see, inserting the data and querying the data. Okay, good, successful. And I will just talk mainly of a couple of different optimizations, especially those that are pertinent to this project. The continuous aggregates. So we can have a materialized view for vehicle hourly summary, and that basically groups the data into 1 hour buckets, which is good for things like reports and dashboards. And this particular series of command, first I'm going to drop the materialized view if it exists, just for demonstration purposes and so we don't hit any unexpected errors. And we have this statement to create it, and this statement, which typically run on the database, is to refresh those continuous aggregates, if necessary. And we have this query to query the results. So as you can imagine, if we try to query the results, we get an error because we haven't created that materialized view yet. Now let's create the materialized view. Okay, it says it ran successfully, and okay, so it didn't exist before, but now we created it, and we should be able to see, okay, we have this materialized view which is displaying that data from the main table in hourly buckets. Okay, the next optimization is compression, and these may or may not be enabled by default. If it isn't, you can enable compression with this SQL, and it's going to be an alter statement on the table, and you have to set the compressed segment by. Vehicle ID would be a good column, and along with the compression you can also apply a compression policy. In this case I'm putting it for 6-day intervals, so that would automatically compress chunks older than 6 days. And this is how those two queries look wrapped in SQL Alchemy, and with some printouts and some verification of the results, a couple of error handling. So we have basically, we see the results that we've enabled compression on the hypertable, and we've added a compression policy along with checking the compression settings and the compression policy from the table metadata information. Now, the last optimization I'll mention is the data retention. This was kind of briefly mentioned in the presentation, but we can add the policy, which is according to business rules. In this case, we were saying 7-day interval. So it's basically going to drop data older than 7 days. In some environments, it's like a regulatory requirement to retain the data for a certain period of time, or even not retain the data for a certain period of time. So we've added that retention policy, and there is a printout that basically shows the results of the verification of the policy. Now, as you can imagine, like the create, the hypertable set, those optimizations with compression and data retention, it can all be done in kind of like one big SQL statement, passing in different like options with or create table as different options, and the materialized view might have to be a separate SQL statement, but if essentially breaking it down allows you to see kind of the series of steps they needed to essentially install and configure the hypertable and start out with some basic optimization. All right, thanks. Bye.